This video is about GMRES, or the convergence of GMRES, and we're going to see what happens when you have what we call an outlier. So we're looking at the convergence of GMRES, and we already know that the convergence is described by this min-max expression of the where we took the minimum of normalized polynomials over the maximum of the polynomials evaluated in the eigenvalues. Okay, you've seen before how to build a convergence bound for this situation where you have eigenvalues localized in some region. What we're going to see now is what happens when we have an eigenvalue not within this disk but quite far away from it. So maybe here, and we're going to call this lambda 1, and this is what we call an outlier. So we have all eigenvalues in some small region and one eigenvalue which lies quite far from it. Okay, normally you would try to find a polynomial which has a small function value in the eigenvalues, and now we're going to, we want to make it small, but we will make it even more restrictive in this construction. We're going to make it 0. So every polynomial with a root in lambda 1 can be expressed in this form, where r is a polynomial of 1 degree less. Okay, we want this polynomial to be normalized, so we divide by lambda 1, and in this way we can also just enforce that r is normalized. So this means that q is in PM0 and q of lambda 1 is equal to 0. We're going to now formalize this idea into using a lemma. So the lemma states that if you assume that all eigenvalues except lambda 1 lies in some disk of radius r, and lambda 2 does not lie in that disk, then star, which is the equation on top, is bounded in this way. And what we see here is, okay, we have some factor here which is independent of m, factor independent of m, and here we have r quotient between r and c, and to some power of m, or m minus 1. And this quantity here is almost the quantity we have in the situation without outliers. So it means that the quotient RC determines the rate of convergence in this bound. So the rate of convergence in the bound with an outlier is actually the same as the rate of convergence in the bound without outlier. But instead, it comes at the cost of a coefficient. But let's prove this. Okay, we specialize the bound for a specific polynomial lying in the set. So we get that if we have the star equation is less or equal to the maximum of all these eigenvalues, and since this is a root, since lambda 1 is a root of the polynomial, we can remove that value and get the same expression but with lambda 2. Okay, and now we use a property of the specific polynomial here. So let's look at the absolute value of q lambda j, where j is somewhere between 2 and n. Okay, so we have this expression, and we take its absolute value of the numerator here. We see that we can add and subtract c, so we get lambda 1 minus c and c minus lambda j, and and we can split this up, so we get lambda 1 minus c and c minus lambda j, and because lambda j is at most distance r from c, we have a bound here, and so we get exactly this coefficient. Okay, since R is chosen freely, we have here just the maximum of this expression where R is a polynomial of degree m-1 normalized. So we can use the standard Sarantonello bound to bound this quantity. So we use the bound that we normally use for without outliers here. And that is the end of the proof.